Okay, girls, I'm going to go through the short answer questions now. So the first question was answered really well in general. There were just a few little errors that people made. I want you to be really careful when you write the chemical symbols. So quite a few people wrote SE, and I know that it was probably just your C with a little bit of a flourish, but you've got to be careful because Se is actually another element called selenium, and so therefore I couldn't give you the mark, even though I could tell what you were trying to say. That doesn't count. Also, because we're talking about atoms, the mass number here couldn't be 24.3, and you can't have 12.3 neutrons either. So they don't really work like that, so they had to be rounded to whole numbers. And then just be careful because a few people made some little errors down here with the number of outer shell electrons. But when you count them out, so remember your electrons should be, because they are neutral, your electrons should be equal to the number of protons. Okay, down to the electron subshell configurations. Most people could get oxygen, most people could get nickel. But remember that chromium is the exception. So if you wrote 3D4, sorry, pardon me, 4S2, remember that can't be accepted because you can't have 2 here when you've got 4 here. So what we have is we have 3D5 and 4S1. What 2 features with Mendeleev did he use? Now, it says 63% correct on this question. It was a mixture of which part of the question you got wrong. So most people could tell me about the properties. You were good at identifying that it was the properties that he used, but it's his atomic weight. I didn't accept number here because he didn't know about atomic number at that stage. He only knew about weight. But then what do we use with the current periodic table? We use the number or the number of protons. Going down to this one, having a look at your periodic table. Sorry, yes. Having a look at your periodic table here, you can see that selenium, which was funny because I mentioned that before, is over on the right-hand side of the steps. So that is a non-metal. Sn is tin, so that's definitely a metal. Sr is strontium, and it's in group 2 as well, so therefore it's definitely a metal. Which one has 5 valence electrons? So silicon has 4 because it's in group 14. Tellurium has 6 because it's in group 16, but astatine is in group 15, so it has 5. Which one ends in S1? If it ends in S1, then we're thinking it has to be a group 1 element. So therefore sodium is, this is a group 2 element, aluminium is a group 13 element. So we're not going to have either one of those there. Going down with our labeled diagrams here, most people lost at least 1 mark. Can you see this thing here? I'm going to highlight it over and over again. You had to be labeled. It must be labeled. If you just drew these pictures, yeah, the pictures themselves are only half a mark each. The other half of a mark was labeling it in some way. Going down to question 6, we have a bit of data from a mental heat treatment practical. You can see what kind of data are we collecting. It has to be qualitative because it's descriptive. Yeah, it uses words, there's no numbers. So therefore this is qualitative data. And that was 1 for saying qualitative and 1 for giving me the reason. Identifying a controlled variable, anything that kept the same. So number of bends, sorry, yes. Number of bends is not accepted because the number of bends is the dV. Okay, and which is the heat treatment used in the first one. So you could bend it once it cooled. Yeah, and it was cooled slowly. So cooling slowly meant that it had to be annealing. You couldn't really say if it was tempering here, but they just said that they heated them and allowed them to both cool quickly and slowly. So this one here, just out of interest, would be quenching. Going down to question 7A, so I'm going to go through 7A, B, C because they had a variety of answers here. So if you're in the same, why is the atomic radius of magnesium smaller than sodium? So you have a look at where magnesium is. Magnesium is in group 2, sodium is in group 1. So therefore the core charge in magnesium is greater. So that was 1 mark for saying that the core charge was greater. Then the other 2 half marks had to do with the fact that you needed to mention that they have the same electron shielding because that equals this, because they have the same number of shells. And therefore, because you've got the same shielding but more core charge in the magnesium, you have a greater pull. So that's where you got your other half mark. So a lot of people could access 1.5 marks or 1 mark, but not that full 2 mark response. So you need all 3 of those points for the 2 mark response. In the second question, why is the first ionization energy of calcium lower than magnesium? So calcium is in group 2 and period 4, magnesium is in group 2, period 3. Okay, so therefore we've got greater electron shielding because there's an extra shell. All right, so that was our first point that I needed there, and that was worth a whole mark to talk about that. Because they're in the same group, they have the same core charge. And the reason I knew to talk about core charge was because that was in the question. It told me to talk about electron configuration and core charge. Therefore, if you've got the same core charge but greater shielding, you don't need as much energy to remove it. So it needed to refer to energy in that final half mark. Lots and lots and lots of you could tell me that francium was the largest element in group 1. Good. You could also tell me that it had the greatest number of shells. But because of that, I wanted you to talk about them occupying a larger volume. Right, so just that last mark there was due to talking, last half a mark, sorry, was due to talking about that larger volume. Oh, the metallic bonding model. Here's another example of how you have 2 marks to do it, but there needs to be a lot of information in there. So a lot of people told me about the cations and they told me about the C of delocalized electrons. And I gave you half a mark for the label, for the diagram as well, without any labels. I don't know why that keeps doing that. Okay, let's just go out and click here, and then it won't be able to do that anymore. But then the last mark, you needed to refer to one of these. So it's quite hard to draw them, but you could label next to it that it was non-directional bonding. You could label next to it that it was a 3D lattice. You could label next to it that it had electrostatic attraction between them. And so lots and lots of people got 1 to 1.5 marks, but couldn't get that last half a mark. So have a look at this list, add them to your diagrams, and then remember that for the next time. Okay, so as we go down, oh goodness. As we go down to the last 2 questions, you can see here, explain with reference why copper is used to make wires. Just referring to its ductility and its electrical conductivity only got you 1 mark. To get the other half a mark for each one of those, you needed to refer to the fact that it had non-directional bonding, then that allows it to be drawn into wires. And I needed the free-moving electrons to be linked to the electrical conductivity. The very last question, only a couple of people managed to flip them around, but you needed to use your periodic table and also your knowledge from our experiment. So gold, completely unreactive. Most people knew that one was there. Iron, not very reactive, so it went there. Magnesium was the highest reactivity you did in your experiment, so it went there. Sodium, we saw a little bit of a pop, and remember when we did potassium and water, it was highly explosive, so that's why we got there. And here's my marking scheme. So if you get all 5 correct, you get 2 marks. 3 to 4 correct, you got 1 mark, but if you only got 0 to 2, I didn't give you any marks at all.